Yeah, hello, dear participants of the ICM. My name is Thomas Schick from Göttingen, and I'm moderator of this session meeting. It's actually 3 sections at a time: geometry, topology, and PDE. And I'm happy to introduce our speaker of today, Richard Bamler from UC Berkeley, who has been a driving force in the exciting developments of Ricci flow and its applications in the recent years. And that's precisely what he's going to tell us today, some recent developments in Ricci flow. So Richard, the floor is yours. Go ahead.
All right. Yeah, thank you, Thomas. It's a great honor to speak here at the ICM. And in today's talk, I want to survey some recent developments on Ricci flow that have occurred over the last 5 years, approximately. Sorry, I hope you can see it. Yeah. All right, so the structure of my talk will be as follows. I'll first give a brief introduction to Ricci flow, and then I'll focus on some recent developments in dimension 3. And then later in part 2 of the talk, I'll talk about Ricci flows in dimensions 4 and higher dimensions, talk about some even more recent developments that may have some further, that may spark some further developments and possibly some further applications. All right, so let me start with the introduction. So if I had to summarize my overall research goal, at least pertaining to this talk, then it would be to use tools in geometric analysis, and in particular Ricci flow, to prove theorems in topology. And we see that very often we have to work really, really hard and for a very long time on the Ricci flow side to then obtain just a few topological results. But I would argue that this is worth the work. All right, with this being said, let me introduce the Ricci flow equation. So Ricci flow is given by a smooth family of Riemannian metrics, GT, parameterized by a time parameter that live on a manifold M. And they satisfy the Ricci flow equation, which reads that the time derivative of the metric is equal to -2 times its Ricci curvature. And this is often coupled with an initial condition. And the reason why we care about this equation is because in harmonic coordinates, this equation roughly takes the form of a nonlinear heat equation in the metric coefficients. Okay, so we can expect that as we evolve a metric under this flow, it somehow becomes more homogeneous, or somehow, it somehow improves in a certain sense. And this equation was introduced by Hamilton in 1982. And in the same paper where this was introduced, Hamilton shows that this initial value problem has a unique solution for some maximal time t. T could be infinite, in which case we say that this flow is eternal. It exists for all non-negative times. Or t could be finite. And in this case, we say that the flow develops a singularity at time t. And this can be detected by the fact that the curvature blows up near the singular time. So here's an example that we should always keep in the back of our minds. When we start the Ricci flow with a metric that's already kind of optimal, meaning that it's Einstein, so the Ricci tensor is a multiple of the metric, then the Ricci flow will just evolve this metric by rescaling. And some of the sign of the Einstein constant decides whether it scales it up, down, or keeps it the same. Okay? So for example, in the case of a positive Einstein constant, you could think of a round sphere that just shrinks down and asymptotically has diameter 0 after some finite time. And you see that here, when it approaches diameter 0, the curvature blows up and we have a singularity. If lambda is equal to 0, we could think of a torus that just stays constant in time. And if lambda is negative, we could think of a hyperbolic surface that expands as we move forward in time. Okay? So this is what happens when we start with a metric that's already kind of optimal. But most often we care about the Ricci flow when we start with a metric that's not very optimal, and we hope that the Ricci flow will take it to some kind of better metric. And so this can be done successfully, for example, in dimension 2, where it was shown that given an arbitrary initial metric on a compact 2-dimensional manifold, the Ricci flow converges, at least modulo rescaling, to a constant curvature metric. And in addition, it preserves the conformal class of the metric. Okay? And so this can, in fact, with a little more work, be used to prove the uniformization theorem, stating that every compact surface admits a constant curvature metric in each conformal class. Okay, so the idea is just you start with an arbitrary metric, you evolve it by the flow, and then in the limit, you obtain your desired constant curvature metric, right? So this would be somehow the first topological or geometric application of Ricci flow, but of course, the uniformization theorem has been known before, and so this proof comes 100 years too late. So if we want to find an application of Ricci flow that hasn't been proven before, we will have to go into higher dimensions. Okay. So with this being said, let me now move my attention to dimension 3. And so when we talk about Ricci flow in dimension 3, what I should say is that the analysis of the Ricci flow equation becomes much more complicated. And in fact, the singularity formation of the flow becomes much more subtle. Okay? And maybe the best way of illustrating the singularity formation is by discussing the famous dumbbell example. Okay, so let me do this on a slide. Okay? So what I do in this example is I look at a topological three-sphere, and I equip it with a rotationally symmetric metric that looks like a round 3-sphere of radius R1 on one side and a round 3-sphere of radius R3 on the other side. And they're connected by a neck of width approximately R2. So what we know in this example is that when we start a Ricci flow from a metric of this shape, then the flow will always incur a singularity. But the type of singularity that we see depends on the choice of the radii R1, R2, and R3. So namely, if we choose the radii comparable to one another, then somehow the concavity of the neck here will somehow contribute a lot of negative curvature, and it will cause the neck to expand until it somehow dissolves, and then somehow the metric will become rounder and rounder and then be asymptotic to a round shrinking sphere. Okay? So if we magnify the flow here, it looks like a round shrinking sphere. On the other hand, if we choose the neck very thin, then somehow the positive curvature coming from the cross-sectional two spheres dominates, and it causes the neck to contract and become thinner and thinner. And in this case, we see this local singularity here, which is some kind of neck that has, asymptotically has width 0. Okay? So if we magnify in this area, then what we see is a flow that looks close to a cylinder, where the S2 factor shrinks down to a point, while the R factor remains constant. And then there's some kind of intermediate case where two of these things occur at approximately the same rate. And in this case, we see some singularity here at the tip. And if we zoom into the singularity, then we see some kind of paraboloid-like solution, which is also called the Bryan soliton. All right, so these are the three different singularity models in the rotationally symmetric case. So what I want to do next is I want to focus on general Ricci flows, at least in dimension 3 for now. And I want to understand the singularity formations of a general Ricci flow. And this is done often using what is called a blow-up analysis. Okay, so a blow-up analysis is a tool that's very common when we study geometric equations. But just for the sake of this talk, let me recall again what that entails and use the example of a Ricci flow here. Okay, so here I tried to draw a Ricci flow. So the x-axis should denote the manifold, and the y-axis should denote time. And the dashed line here should denote the fact that this flow develops a singularity at time t. So since we have a singularity, we can find a sequence of points xi and times ti, such that the curvature along these points goes to infinity. Okay? So we also say these points xi, ti run into a singularity. Okay? And then we would like to understand the geometry near these points. And we do this by first choosing a sequence of rescaling factors, lambda I, and then we parabolically rescale the flow. So we rescale distances by lambda I and times by lambda I squared. This somehow preserves the Ricci flow equation. And we also apply a time shift ti such that this time ti corresponds to time 0. Okay? So in doing so, we're constructing a sequence of Ricci flows that are defined on larger and larger backwards parabolic, backwards time intervals. And then we can hope, due to some, let's say, compactness theorem or something like this, we can pass these flows to a limit. And in the end, we obtain some flow that's defined for all non-positive times. And this is called, this flow is often called a singularity model or a blow-up model. All right, so the upshot here of this construction is that a blow-up analysis allows us to reduce the study of the singularity formation to somehow the classification of possible singularity models. Okay? And this was, in fact, done successfully by Perelman in his groundbreaking paper. And in this paper, he showed that the only possible 3D singularity models are either the sphere, the round sphere, or a quotient of it, or they're cylindrical, or they are the brine soliton. Okay, so these are exactly the 3 different models that I've shown you in the rotationally symmetric case. So there are no more singularity models if we don't assume rotational symmetry. And I should say that Perelman only obtained a more qualitative description in the 3rd item, but this was later clarified by Simon Brendle, who showed that the last item has to be the brine soliton. All right, so this theorem now tells us, combined with the blow-up analysis, that at points that are close to a singularity, in the sense that the curvature, at points where the curvature is very large, that the local geometry looks somehow close to being spherical, cylindrical, or brine soliton-like. And so this observation then allowed Perelman to construct what is called a Ricci flow with surgery. Okay? So a Ricci flow with surgery is given by a sequence of Ricci flows parameterized by consecutive time intervals that are defined on manifolds of potentially different topology. And these Ricci flows are related to each other via a surgery step. Okay? So the definition of the surgery step is quite technical, and it fills about 1.5 pages. So it's a bit too much for this talk. But so instead of showing the definition, let me just show you a movie here. Okay? So I start with some initial conditions, some initial metric on a manifold. And then I evolve this metric via the Ricci flow. And maybe I incur a singularity. And let me just stop kind of short of the first singular time. So I may see this kind of cylindrical regions occurring. And what I do now is I locate small cross-sectional 2 spheres. I cut along these 2 spheres and I glue in 3 disks that I endow with some nice geometry. Okay? So in doing so, I've changed the topology of the manifold in a controlled way, but I've also made some of the geometry less singular. And this allows me to run the flow again until I hit another singularity. Okay? And so maybe here I see the same type of singularity. So let me just perform the same construction. And here, let's say we see some kind of spherical singularity. And in this case, I just say that Ricci flow has done its job and just discard this component. Okay? And then I run the flow again, and so on and so further. Okay? And Perelman showed that this kind of process can be continued for as long as you want. Okay? So this flow then led Perelman to deduce 2 very important topological applications. The first one was the Poincare conjecture, stating that every simply connected 3 manifold has to be the 3 sphere. And also the geometrization conjecture, which classifies 3 manifolds up to their hyperbolic pieces. Okay. So as you can see, this Ricci flow with surgery was an extremely powerful tool in studying the topology of 3 manifolds. However, I would claim that this construction had a drawback. And the drawback was that the surgery construction is not canonical. By this, I mean it depends on several surgery parameters for which there doesn't seem to be a canonical choice. So for example, the surgery construction depends on the size of the surgery scale delta at which I cut the cross-sectional 2 spheres, and that just doesn't seem to be a canonical choice for delta. So delta has to be small for the construction to work out, but positive. And there's no small and positive number that's canonical. Then moreover, it somewhat depends on the location of the necks where we perform the surgery. And even worse, if we somehow went back in time, let's say at time t1, and decided to perform the surgery somehow slightly differently, then this could a priori completely change the evolution of the flow later, and also the space of possible surgery parameters. So there are many, many Ricci flows with surgery starting from a given initial condition. And even Perelman noticed this disadvantage, and in both of his papers, he wrote a comment. So for example, in his first paper, he wrote, "It is likely that one would get a canonically defined Ricci flow through singularities, but at the moment, I don't have a proof of that." All right, so then more recently, first in John work of Kleiner and Lott, and then Bruce Kleiner and myself, we proved Perelman's conjecture, or we answered Perelman's question. So let me first say abstractly what we did, and then let me go into more detail on the next slide. So abstractly, what we did is we showed that there is some reasonable definition of a weak Ricci flow through singularities, meaning a flow that somehow flows through singularities on its own without us having to interfere and having to perform a surgery. And within this class, we have well-posedness of the Ricci flow equation, meaning that given an initial condition, there exists some one of these flows starting from this initial condition, and it's uniquely determined by the initial condition, and we have continuous dependence on the initial condition. Yeah. And again, I'll say a bit more about what this means in practice on the next slide. But before doing so, let me briefly digress and let me compare the situation with a close cousin of Ricci flow, namely the mean curvature flow. Okay. So the mean curvature flow concerns the evolution of embedded hypersurfaces, often in Euclidean space. And very often we can learn certain things from mean curvature flow, or mean curvature flow can learn certain things from Ricci flow. So it's very useful to make this comparison. Okay? So we could add, and I should also say, if I had to draw some pictures of an evolution of mean curvature flow, then they would look very similar to the pictures on the previous slide. Okay, so they're very, very related. So we could ask, well, is Perelman's conjecture true for a mean curvature flow? And well, first of all, we could ask, are there kind of weak flows through singularities? And the answer is a clear yes. So there have been known for a long time, there have been known two flows called the level set flow and the Brachy flow that somehow flow through singularities on their own. And they can somehow be defined because this is an embedded flow. So we can use the ambient space to define a level set flow through some kind of viscosity principle, or the Brachy flow through some kind of weak integral principle. However, if we ask about uniqueness, then the answer is no in the general case, because there's some phenomenon called fattening, which is associated to non-uniqueness. Okay? So for general mean curvature flows, Perelman's conjecture would be false. However, if we restrict to the mean convex case, then it was proven by White that there is that there's no fattening, which is equivalent to being uniqueness. Okay? So Perelman's conjecture would be true in this case. And then even further, if we restrict to the even smaller subclass of two convex mean curvature flows, then we have uniqueness and existence. And there's also some construction of a mean curvature flow with surgery. And it turns out that this weak flow can be approximated by mean curvature flows with surgery as we choose the surgery scale smaller and smaller. Okay? So let me now go back to Ricci flow. So first of all, I should mention that these two types of flows cannot be defined for Ricci flow because they really leverage the fact that these flows are embedded in an ambient space, and that's not the case for Ricci flow. However, we can somehow get some inspiration from the third item here, so the fourth item here, and construct some kind of singular Ricci flow by approximating it by Ricci flows with surgery. And this was indeed done in work of Kleiner and Lott. So in this work, they showed that there is a weak singular Ricci flow starting from any initial condition. Okay? And they did this by constructing a sequence of Ricci flows with surgery with smaller and smaller surgery scale, and then applying a compactness theorem and showing that in a certain sense, these Ricci flows with surgery converge to some nice singular flow in the limit, or subsequently converge, right? So here's some kind of picture of a weak singular flow. So what you should imagine here, and I try to draw some time slices here, is that we see this kind of cylindrical region that pinches down to this kind of singular double cone at the singular time. And then immediately this double cone resolves and becomes these two bows. Okay? So this is somehow reminiscent of Morse theory, for example, so level sets in Morse theory. Okay? So this gives some kind of a nice picture, and it looks like this flow is more canonical because it doesn't look like we are interfering with the flow. However, this flow was obtained using a compactness theory, and so therefore it's not clear whether this is the only such flow for a given initial condition. So there could be many ways of resolving the singularity a priori. However, the fact that this is not the case was then later shown by myself and Bruce Kleiner, where we showed that this flow is in fact uniquely determined by its initial condition and also depends continuously on it. So in other words, if we change the initial condition in a continuous manner, then the associated singular Ricci flow also changes continuously. All right. And then moreover, I should also say that the definition of a singular Ricci flow is actually much nicer than the definition of a Ricci flow with surgery. It fits on half a page. It's still a little too much for this talk, so let me just say approximately what it is. So essentially, a singular Ricci flow is given by some kind of four-dimensional space-time manifold that is equipped with some smooth structure and such that locally this manifold looks like a Ricci flow, but globally it may have some non-trivial topology. Okay? And more importantly, this flow, despite its name of a singular Ricci flow, is a completely smooth object. And the reason for this is that we're actually just defining the flow on the regular part. Okay? So we can't really make sense of the Ricci flow equation on the singular part. So it's really not important to say what the flow does on the singular part. And instead, we somewhat describe what the flow does asymptotically near the singular part. Okay? So this is different from what is done in mean curvature flow. All right, so this, in my opinion, gives a satisfactory picture of Ricci flow in dimension 3. And moreover, it had some interesting topological applications because it allows us to somehow run geometrization for families, continuous families of metrics. Okay, so let me present two of these applications here. So the first application concerns the space of all positive scalar curvature metrics on a closed 3 manifold, so equipped with the C-infinity topology. And our result shows that this space is either empty or contractible. So in other words, if M sat admits a positive scalar curvature metric, then the space has to be contractible. Okay? And these type of questions go back to work of Hitchin in the 70s and then Gromov and Lawson, who showed that in higher dimensions, these spaces have some kind of non-trivial topology. So our result is some of the first one in kind of lower dimensions, which is non-trivial, where we show that this space has trivial topology. And then there's also a nice link between spaces of metrics and diffeomorphism groups that we can exploit. And this allowed us to prove the generalized Smale conjecture, which states that the space of diffeomorphisms on a spherical space form is homotopy equivalent to its isometry group. Okay? So this was known for the 3-sphere, not where gamma is equal to 1. This was proven by Hatcher, and it's also called the Smale conjecture. And it was also known for a few other spherical space forms, but somehow the conjecture in its entirety was unknown up until recently. And so we can somehow give some uniform treatment for spherical space forms, and then for some other manifolds, such as hyperbolic manifolds and infranil manifolds. All right. Okay, with this being said, let me now move to higher dimensions. Okay, so now as we move to higher dimensions or talk about higher dimensional Ricci flows, I should say that except for two special cases, namely Ricci flows that admit relatively strong positive curvature conditions, or Kähler Ricci flows, very few things have been known about Ricci flows up until recently. And in particular, if we talk about general Ricci flows, we hardly knew anything about their singularity formation. Okay? So we really have to start from the beginning here, and we have to ask ourselves, what are possible singularity models for Ricci flows in higher dimensions? Well, luckily, there are some very clear candidates for singularity models in higher dimensional Ricci flows, and these are called gradient shrinking solitons. So a gradient shrinking soliton is given, so let me spend the slide explaining what a gradient shrinking soliton is. So a gradient shrinking soliton is given by a Riemannian manifold that's equipped with a potential function f, and it satisfies this gradient shrinking soliton equation, so which is essentially the Einstein equation, but we have this extra Hessian term here. And so the reason why we care about this equation is because we can take a metric of this form and turn it into an associated self-similar Ricci flow. So what we can do, namely, here is we can take the flow of the gradient vector field of f, and we can pull back the metric via this flow and then multiply by a time parameter. I look at this for all negative times. And this gives us a Ricci flow that somehow scales down modulo diffeomorphisms. So one example would be the round sphere. In this case, f would just be chosen to be constant. So this term goes away. And then the corresponding associated Ricci flow would just be the round shrinking sphere that becomes singular at time 0 and exists for all negative times. Okay. Maybe a slightly more complicated example would be a round shrinking cylinder. In this case, we just take a Cartesian product of a round sphere and a Euclidean factor. And in this case, somehow, and f would be a quadratic function, so that the Hessian here makes up for the lack of Ricci curvature. And the way we should think about this here is that somehow the spherical factor contracts under the Ricci flow, and the Euclidean factor remains constant. But however, modulo diffeomorphisms on the Euclidean factors, modulo dilations that are generated by the gradient of f, the flow somehow contracts all directions also as well. All right. So then there's some more complicated gradient shrinking solitons. There's a whole zoo of them. Okay. So one important observation about gradient shrinking solitons is that if we look at their associated Ricci flow, since it's self-similar, any blow-up limit of the self-similar Ricci flow is just the same Ricci flow again. Okay. So this shows us that every gradient shrinking soliton has to occur as a singularity model of at least its own flow. And then vice versa, there has been a long-standing conjecture that somehow the opposite should be true in a certain sense. Okay? So in a certain sense, for any Ricci flow, if it becomes singular, most singularity models in a certain sense are given by gradient shrinking solitons. Okay? And I call this the Folklore conjecture, but this has been implicit in work by Hamilton from the 90s, and some similar statements are true for other flows, such as the mean curvature flow. So this is a very reasonable thing to expect. Okay, and so what I want to do in the next few slides is now show you that this conjecture is true and show you in what, and hopefully you agree with me that this is an optimal sense, in what sense it is true. Okay. But all right, before doing so, let me first discuss some examples just so we can adjust our expectations. Okay? And so the first example is due to a former graduate student of mine, Alexander Appleton, who constructed Ricci flows in dimension 4, whose blow-up limits he can completely understand. Okay? And these blow-up limits are the following. They're either the Iguchi-Hansen metric, which is a Ricci flat asymptotically conical metric, or it's R4 modulo Z2, so Euclidean space modulo the antipodal map. So this has an orbifold singularity at the origin, or similarly the Bryan soliton modulo Z2, or the quotient of a cylinder. Okay. So these two spaces here are Ricci flat. These two spaces are singular. They have an orbifold singularity, an isolated orbifold singularity. And then with respect to the Folklore conjecture, the only gradient shrinking solitons are these two spaces. Okay. So you may have noticed that I put the last two singularity models in parentheses, and that's because in Appleton's work, it is not clear whether all 4 models occur or whether only the first 2 models occur. Okay. And so while we don't know which one's the case, it's conceivable that there are cases where only the first 2 models occur. Okay. And in particular, then the only gradient shrinking soliton that's predicted by the Folklore conjecture would be a singular one. It would have a singular point. Okay. So somehow this observation was reinforced by work of Stolarski in higher dimensions and Li Tian and Zhu in the Kähler-Ricci flows. And this leads us to revise the Folklore conjecture, okay? So it shows that, let me still keep the beginning somewhat vague, that the most singularity models are possibly singular gradient shrinking solitons, where the singular set has codimension at least 4. And so in Appleton's example, the singular set is a point in something 4-dimensional. So that would be some of the optimal case. All right, so let me now focus on proving this Folklore conjecture. And so to do this, I need to recall the blow-up analysis that I mentioned in the beginning of my talk. Okay, so again, we assume we have some Ricci flow here that becomes singular at time t, and we take a sequence of rescalings, parabolic rescalings, and we want to pass to some singularity model. So in dimension 3, this was no problem because the singularity model ended up being smooth anyway, and then some of the type of conversions can be defined quite well. However, as we've seen in the previous slide, in higher dimensions, the singularity model might be singular itself. Okay, so we can't just put some singular space here. We can't just put some smooth Ricci flow here. We need some kind of singular Ricci flow for the limit. Okay? So one question that we need to answer in order to prove the Folklore conjecture is to say what kind of singular Ricci flows we expect to be here in the limit. Okay? And then once we have these singular Ricci flows defined, we also need some kind of topology for the convergence that happens here. And we also need some compactness theorem that allows us to extract a subsequential limit. And lastly, this flow, if it's a singular Ricci flow, may be very irregular. So we need some kind of partial regularity theory that allows us to say that this limit is kind of smooth away from some small singular set. And so before answering these questions, let me draw the analogy here with Einstein metrics, where things are better and have been better understood. Okay? So Einstein metrics are a special case of Ricci flows, so we definitely have to understand those. Okay? And so this is now work that goes back to work of Gromov, Chigger, Kolding, Tian, Neighbor, and also ideas of Anderson, Nakajima, and so on. Okay, so let me just allow me to do this digression here. So let's suppose we have a sequence of complete and pointed Einstein manifolds. Then it has been known by Gromov that we can pass to a subsequence and that we have pointed Gromov-Hausdorff convergence to some pointed metric space in the limit. Okay? So this is the standard Gromov-Hausdorff compactness theory. So now this limit could be, hypothetically, could be very irregular. However, it turns out that if we impose some non-collapsing condition on the sequence, for example, by saying that the volume of a ball of some fixed radius around the base point is uniformly bounded from below, then in fact, the limit is quite nice. It is smooth, so given by a smooth Riemannian manifold, away from some singular subset whose codimension is at least 4. Okay? So this shows that it's really enough to study this Riemannian manifold on the regular part then. And so you may have noticed similar theories for other geometric equations, such as minimal surfaces, mean curvature flow, harmonic maps, and harmonic map heat flows. And the reason why these similar theories exist is because these kind of partial regularity theories here, they really just depend on a few very basic ingredients, and they can be verified for all of these geometric equations. And then there's some kind of machinery that allows us to combine these ingredients and to deduce a partial regularity theory. However, such a similar theory for Ricci flow has not existed for a long time, because mainly some of these standard ingredients were not available, at least a priori, in the Ricci flow setting. And secondly, some of these notions like Gromov-Hausdorff convergence or metric space have not had some kind of parabolic version for Ricci flows. Okay? So what we needed to do to somehow generalize this theory for Einstein metrics to the Ricci flow case was to come up with some new notions of Gromov-Hausdorff convergence or metric space in the parabolic sense, and also to find a way of proving partial regularity that bypasses some of the lack of these standard ingredients. Okay? So, but nevertheless, this was possible. And so now we have a compactness and partial regularity theory for Ricci flows that really mirrors this one for Einstein matrix. Okay? So let me state this here briefly, or just very shortly here. So again, let's suppose we have a sequence of Ricci flows, and let me assume that the base point here lives in the final time slice. Then there's a subsequence that F converges. So this is a new notion. It's some kind of parabolic version of Gromov-Hausdorff convergence. So I had to define this new. And F converges to a metric flow, which I'll call X, script X, right? And again, a metric flow is a parabolic version of a metric space. Again, a new definition. So again, this metric flow may a priori be very irregular. However, if we impose a non-collapsing condition, which is now expressed in terms of the pointed Nash entropy at the base point. So this is somehow related to Perelman's W functional, or his mu entropy. And that's a condition that's really ubiquitous in Ricci flow. So we have that very often. Then the limiting metric flow is smooth away from some singular subset S of codimension at least 4 in the space-time sense. Okay? And so here, since it's a parabolic, we have to assign 2 points to the time direction, which is kind of natural. Okay? So this is really analogous to the theory of Einstein metrics. Okay? And also on some other regular set of X, the flow is really given by some kind of smooth Ricci flow space-time structure, just like in the 3-dimensional case. So really everything seems to fit together here. All right. Okay, so now it turns out that this compactness and partial regularity theory for Ricci flows is really at the heart of this folklore conjecture, at the heart of the proof, right? So here's now how we resolve the folklore conjecture. So first, again, here we want to take a blow-up limit. And as we said before, we have to replace this limiting Ricci flow by a metric flow. And we have to replace convergence by F convergence. Okay, so we take this blow-up limit, and this blow-up limit may be a metric flow that is smooth away from some codimension 4 singular set. And we could ask, is this a gradient shrinking soliton as sought in the folklore conjecture? And well, the answer is no. That's not even true in dimension 3. However, there are several ways how we can see gradient shrinking solitons in this picture. And maybe the most common way would be to take blow downs. Okay. So remember, this is a flow that's defined for all negative times. And so now what I do now is I scale this flow down. Okay? I make it smaller, scale distances down and times down. And this will approximate what the flow X does then at time close to time minus infinity. Okay? So that's why I call it the limit X minus infinity. So I can take another F limit here and I obtain another metric flow that has the same partial regularity properties. Okay. And then what can be shown then is that the revised folklore conjecture is true in the sense that this blow down limit of the blow up limit is given by a gradient shrinking soliton, or is the associated flow of a gradient shrinking soliton with a possible codimension 4 singular set. And even better, in dimension 4, M is actually a smooth orbifold with isolated singularities, just like in Appleton's example. Okay? So the blow down of a blow up is a gradient shrinking soliton. Or in other words, I could also somehow adjust these lambda i's slightly, make them slightly bigger in every step. And if I do this carefully, then I could even see a gradient shrinking soliton in the first limit. All right. Okay, so this proves the folklore conjecture and some other conjectures that I don't have time to get into. But so what I want to do in the next 2 slides is I want to give you some kind of idea what kind of new philosophy enters this partial regularity result, or compactness and partial regularity result for Ricci flow, because there are some observations that were important. And to do this, I'll do this by telling you, giving you an idea of the definition of a metric flow. Okay? Again, a metric flow is a parabolic version of a metric space. Okay? All right, so let me first recall that if we have a Riemannian manifold, then there's a standard process of turning this into a metric space. We just take the length metric. And when we have a metric space, then we can take Gromov-Hausdorff limits or do certain things that have to do with synthetic spaces. Yeah? And so this is a similar process that we want to replicate for Ricci flows. So we want to take a Ricci flow, and similarly, we want to pass to a metric flow. Okay? And so we do this now as follows. So this should be a synthetic object. Okay? So we do this as follows. So we first take the length metric of every metric t. So this gives us a family of metric spaces that may a priori have nothing to do with one another. And then I will relate these metric spaces by looking at the conjugate heat kernel of the heat equation coupled with the Ricci flow. So this is a linear equation, and so it has some kind of heat kernel, which somehow gives me a probability distribution at earlier time slices. Okay? So this can be recorded by a probability measure on a metric space. Okay? And so these two pieces of data are the data that make out a metric flow. Okay? And so then I just impose some compatibility conditions. Okay? So the way that you can imagine this is that for every point at a later time slice, you fix some kind of probability measure at an earlier time slice. And this gives you some kind of relation between different time slices. Okay? And so here's some of the interesting observation. The observation is that this construction forgets world lines. So in other words, if I take a point here at time t, then I can't tell, once I've passed to a metric flow, I cannot tell what the corresponding time at an earlier time, what the corresponding point at an earlier time was. All I have is some probability distribution of some of the likely past of that point. Okay? And this was somehow an essential idea that we somehow do away with this concept of world lines. Okay? So I'm running short of time, so let me just briefly discuss one example where this somehow becomes important, and this is the example of the Bryan soliton. So again, Bryan soliton is some rotationally symmetric solution to the Ricci flow. It's a steady soliton, so all time slices are isometric. And so this could occur as a blow up of a singularity. And so now I could say I want to take blow downs and I want to identify the corresponding gradient shrinking solitons. Okay? So let me take a base point here at time 0 and take blow downs of this flow. Okay? So I could look at this naively and could say, well, every time slice, it's just the Bryan soliton. And if I scale it down, it just becomes flatter and flatter. So in the limit, if I take my Gromov-Hausdorff limit fixed at the base point here, then I should get a ray. However, here I've implicitly used the concept of world lines because I've taken limits at earlier times that were based at the same point as the base point that I've chosen at time 0. And that's something that I'm not allowed to do anymore. Okay? So instead, what I have to do is I have to look at the conjugate heat kernel starting at this point, and I have to follow this backwards in time. And it turns out that this conjugate heat kernel is concentrated in a region that looks more and more cylindrical. And therefore, the blow down of this Bryan soliton is a round shrinking cylinder. All right, so let me just quickly give you a brief outlook, what I expect that we can do next. Okay? And so to motivate this, let me just give you one quick application of the theory from the previous slides in dimension 4. And this application shows that every finite time singularity of 4-dimensional Ricci flow is either modeled on a compact gradient shrinking soliton. So in this case, we can say something about the topology of this of the underlying manifold, or it is at least somewhere modeled on one of the following 3 singularity models, either on a round shrinking, a round cylinder, or a quotient of it with a 3 sphere as a cross section, or a round cylinder with a 2 sphere as a cross section, or a cone over a link that's diffeomorphic to a connected sum of spherical space forms and copies of S2 cross S1. So at least somewhere that's what the singularity looks like. This is kind of the regions that are responsible for the singularity formation. And this...
But, if you speed up, please.
Okay. And so this, let me just show you this, and that somehow motivates the conjecture that there should be some singular Ricci flow through singularities in dimension 4 higher, and the topological change should occur along 2 cylinders or cones. Okay? And this is, in my opinion, a very interesting conjecture, and there may be some interesting topological applications. For example, about classification of PSC manifolds, or very speculative, the 11/8 conjecture. Okay? So maybe I'll stop here. Thank you very much.
Thanks a lot. Yeah, I hope all enjoyed the talk as much as I did. So yeah, with this, we have interesting work to do in the future. So we hope to see Richard again in some later time telling us about the solutions of these conjectures. And I think I close this talk for now, and we move on to the further sections where we want to be in a couple of minutes. Okay, thanks again, Richard, and goodbye.
Thank you very much. Bye.
Okay.